In this video, I'm going to step back from the details of the functions operating on lists that we've been designing and give you a more abstract way of looking at those functions. Now, what do I mean when I say abstract? Well, I mean a view of those functions that's less detailed but still captures their essential structure and still tells us something important about what they do. In this video, I'm not making any changes or additions to the design recipes. You're still going to design functions that operate on lists the same way. What this video does do is gives you a new perspective on why those functions work and how their template sets them up to work. And so what I want you to do is take this material now and maybe watch it again once or twice in the next couple weeks. And I think it'll really help you designing functions that operate on all kinds of arbitrary size data to understand how those functions work and what their templates do for them. So far this week we've seen two list types, list of string and list of number. Both of them have well-formed self-reference. Because of the self-reference in the type comments, both of them also have a natural recursion in the template functions. In fact, these two types are very similar to each other. They really only differ in the name of the type of value included. Strings in one case, number in the other case. So for what I want to talk about now, we can just look at one of them. We'll just look at list of number. And again, we see that it has a self-reference in the type comment, which leads to a natural recursion in the template. What I want to do now is look for a minute at how the three functions we've designed so far each fill the different holes in the template. Here's what I mean by that. If we look at sum on the left and the fun for list of number template on the right, then we look at what I've called for now the red hole in the template. I'm going to give it a better name in a minute, but for now we'll just call it the red space in the template. In the sum function, the red space gets filled with 0. The green space gets filled with plus. Nothing changes in the blue space. We just leave it the way it was. Count starts off quite similar to sum. It fills the red space with 0, the green space with plus, but it changes what happens in the blue space. Whereas in sum, we add the first of ln into the natural recursion. In count, we just add 1 into the natural recursion. Now let's look at contains UBC. In contains UBC, the red space is false. And look what I've done here with the blue and the green. For the blue, I've said that what happens in this function is that it wraps string equals question mark to UBC around first of loss, and I'm calling that the blue. And I've got green stuff both before and after the blue. It's that if expression with its true answer and its false answer. Why am I doing that? Well, here's why. Let me now talk about the name that I want to give to each of these three spots in the template. I'm going to call the red spot base, because really what's sitting in the red spot is the base case result of this function, what the function produces in the base case. For sum, the base case result is 0. For count, the base case result is 0. And for contains UBC, the base case result is false. That's fairly straightforward. The blue I'm going to call the contribution of the first, or the contribution of the first to the overall result. So in the case of sum, each first element of the list, or each element of the list, when it's its turn to be first, contributes itself to the overall result, because sum is sitting there adding together all the numbers in the list. Now, how does that contribution work? Well, that's what combination means. Combination refers to the way in which the final function combines the contribution of the first with the result of the natural recursion. So in the case of sum, the combination is to add the contribution of the first, which is itself, to the result of the natural recursion. Let's look at count for a second. We already saw that the base case result of count is 0. What's the contribution of first in the case of count? Well, it's 1. When we count the number of elements in the list, we don't care what each element is. We just care that it exists. So each element contributes 1 to the overall result. And the combination is still a plus. Now that we understand better what the blue and the green are, the contribution of the first, and the way in which that contribution is combined with the natural recursion, now you can see why I colored things the way I did in contains UBC. The contribution of the first is just to say, is the first element of the list equal to UBC? And the combination is to say, well, if the contribution of the first is true, then produce true. If the contribution of the first is false, then produce the natural recursion. Now, why am I talking about this now? After all, you've just designed 3 list functions. This may seem a bit too hard for right now. The reason I'm doing this now is to give you a bit of a preview of something we're going to do in a couple weeks. In a couple weeks, you're going to see that because we've been working really systematically with well-formed type comments, which produce templates in a well-defined way, so that a lot of our functions that operate on lists and other arbitrary size data have a common form, it's going to be possible for us to write functions like sum and count and contains UBC really in just one line of code. You'll write them by basically talking about how to fill the spaces in this table. Now, we're not ready to do that now. And I'm not trying to say that you need to do that now. You don't need to be able to design one of these functions just by filling in the table. The reason I'm showing you this now is so that when you design these functions the way we've talked about this week, you follow the whole recipe and you write out the template in detail and then you fill it in based on the examples. Maybe when you're done designing the functions, think for a minute about how that function's row in this table would look. And I think that'll help you, as we go on, form a more general view of what these functions are, so that in a couple weeks when we get to what's called function abstraction, you'll really be ready to see how it simplifies the writing of these functions.